Now let's have a look at the effect of heat treatment on the structure. Now there are different types of heat treatment. All the heat treatment, the variable that we change is the cooling rate of cooling, and the medium of cooling. The rate of cooling can be fast, medium, slow. The cooling medium can be either air, water, ice baths, salt baths. It can be like engine oil, like which are very high in carbon content. So that will change the microstructure. Now let's have a look at the annealing. Annealing is properties, a type of heat treatment which returns the microstructure back to its undistorted structure. This affects restoring the ductility. So if you perform any type of heat primary forming or secondary forming process which reduce the ductility of the component, you can actually perform the annealing process, which will remove the internal stresses and make the material more ductile. Now we do not want we don't want always the material to be soft. So we want the material to have a little bit strength in it. So in that case, we will perform a different treatment. Main idea of the annealing / or tempering, which is a different process, is to remove the internal stresses which occurs or which are embedded into the structure after performing usually cold working, after performing machining operation, or so on. Now normalizing is we heat the material to a certain temperature and then we cool it in normal air. We can have an accelerated normalizing where we actually put a fan or cold air in the front. Now, initially for every heat treatment, we have to enter the single phase region, which is above 910 degrees centigrade. Okay. Now, the steel is air cooled when we perform the annealing for the steel to reform a BCC cubic structure, and it get rid of its residual stresses as well. Sometimes we perform the heat treatment to harden the material. We heat the material to a certain temperature and we perform a quenching process. So rather hardening, let's call it quenching process. We quench it in salt bath, we quench it in water, or we can quench it in oil. If we got a pure metal, usually the hardening will not take place. They are not prone to hardening. We have to add some other elements into. Now, if we talk about the hardenability is a measure of the depth of the hardness that can be achieved by performing a heat treatment. If there is a component that has high surface area to volume ratio, like they are flat component, they can be hardened, high hardenability can be achieved. But if there is a component which are quite thick, then in that case it's quite difficult. Then there is a process of case hardening. Case hardening is only we want the skin of the material to be hardened. Multiple types of case hardening process are there. For example, if you want to perform the case hardening on a type of steel, we want only the surface to have a high content of the material that are harder, for example, high carbon content. So we perform a type of case hardening technique known as pack carburizing. In pack carburizing, you have a container, a metal container. Take a metal container. In that metal container, what you do is you put the crushed carbon, graphite powder in it. And then you put the material or the specimen that you want to case harden inside. And then you just like cover it, usually with aluminum wrapping. Just put that powdered material and then wrap it with aluminum casing. And put that in a furnace, in an oven, at like 200 degrees centigrade, at 500 degrees centigrade. The higher the temperature, better the results. What will happen over a period of time is the carbon from that graphite will actually try to infuse into the casing, into the surface. And if you take it out after a day, 2 days, 3 days, the longer you leave, the more depth, case hardening depth is achieved. If you increase the temperature, better the results, more hardened the material is, more case hardening is achieved. That's one type of the case hardening. There is an induction case hardening as well. There's a nitriding as well. There's a carbonitriding as well, where we mix different types of hardening fluids. Then we got tempering. It's used to increase the toughness, but it's used to relieve the internal stresses. How we do that one? We heat the material to a temperature below the critical point where the crystal structure can take place, and then we allow it to cool at a certain cooling rate, hence the process tempering. If we do too quick tempering, too quick cooling, there will be stresses. So we want to make sure the cooling is a slow process. Now, let's have a look at the welding. When we perform the welding, obviously, we heat the material in a very localized zone. So the material is being heated in that very localized zone, and the material has been welded as well. So what's actually happening is the material might be molten here, but next to that material, like on the left and the right, the material is heated to a very high temperature, but it does not convert into liquid. So what happened in this case? There's a thing called HAZ. There's a thing called HAZ, the heat affected zone. So heat affected zone is created. So this is the fusion zone, the weld metal. And then next to that one here and here, this is known as the heat affected zone. If I measure the properties, if I grind that one and take the properties, I will have a different properties in the original structure, different properties in the fuse zone or the weld metal, and the different properties in the HAZ. Now, the further you are away from the fusion zone, the properties are likely to be the same. So the properties here maybe are same to the properties here. The closer you get to the HAZ or the original the fusion zone, the properties are highly likely to change. So if you have a look at that one, further away from here, the original temperature is same. Yeah, it's not much variation. But as you get closer to the heat affected zone, the temperature of that metal is affected. Hence, the microstructure will be different. If you are looking into fusion zone, that's the molten part because the material has to melt and then resolidify. So it's like that might have the same kind of structural growth as the casting. We do not put water on the welded structure. The reason is if you put water on the welded structure, it will form internal stresses straight away. The stresses might be so strong that that material here the welded structure will become super weak. The best way is to provide a very low cooling, which will result in tempering. And this is why the old Japanese, the katana sword, when they make it, when they cool it down, they put like a finely grained mixture of sand or clay on the top, so which will actually reduce the cooling rate to such that it give you the maximum strength and maximum toughness. Okay, now if we have a look at the properties of the welded structure, if you look at the hardness values will be different at each and every point. The melt zone if we are traveling towards the melt zone, towards the top of the melt zone, the hardness value will be less. As you come down, the hardness value will increase. The HV mean hardness weaker, weaker hardness. If you have a look at the microstructure growth, you can see here, they are like dendrites, they are grown inward. So the microstructure has grown inward and inward, so it's columnar grain. This one is if you're welding on the top, just the top bit, you can actually see they are still, columns are being formed in that direction.
Did you just get a warning for low back today?
Say again? Today? Charged. Was it?